Okay, let's start. Welcome to the lecture. So we'll first briefly review this last lecture on introduction to machine learning, especially the binary classification metrics. So this figure explains the concept of true positive, false positive, and true negative, false negatives, and defines precision and recall. So here's an example for a medical, for example, a medical diagnosis test. This particular set of numbers results in these metrics for precision and recall. And for another test that trivially gives everyone a negative decision, negative diagnosis, actually has a higher accuracy than the previous one, which means that accuracy is not always the best metric for evaluating classifiers. So I added a figure on this slide to explain better the concept of false positive rate versus true positive rate. So binary classification is typically based on a decision threshold parameter shown here. So suppose here the horizontal axis is a set of features, could be multidimensional, could be very high dimensional, but I just draw it as one dimensional for illustration. And this distribution is the negative data items, say the set of people who are healthy. And this is the distribution for the positive data items, say the set of people who are sick. So you can set a threshold for the diagnosis. This threshold, if it's set to be lower for the positive diagnosis, then it will have higher false positive rate and higher true positive rate, and vice versa. So you can imagine the figure, this threshold divides the decision boundary, is the decision boundary, and any items to the right of the threshold is predicted as positive. So this particular region is the a true positive. So this region with this shape is true positive. But this little piece from the negative data items, but is diagnosed as positive, predicted as positive. So this is the false positive piece. Similarly, this brown piece is the false negative piece. So you can imagine moving the decision threshold to the left with a lower threshold, then the false positive rate, which is this piece divided by the false positive plus true negative, divided by this whole thing under the negative curve is the false positive rate. The true positive rate is this large piece divided by the whole area under the positive curve. So if you move it to the left, you will increase both. So imagine the threshold is over here, then both rates will be true positive rate and false positive rate will be 0. That's this point. As you move it gradually to the left, maybe in here, then the true positive rate will go up, while the false positive rate is initially still 0. Initially still 0, and gradually you have false positive rate higher than 0. And as you move it gradually more and more to the left, you will have this curve, IOC curve of FPR versus TPR. So the ideal IOC curve is when you have always a 0 false positive rate, FPR is 0 and TPR equals 1. Then LC is equal to 1. But if you have the worst case is when the FPR is equal to TPR, that's this curve. So this happens when when the positive item distribution and the negative item distribution look exactly the same. So if these two are coincide with each other, then your AOC is equal to 0.5. Then you cannot distinguish between the positive or negative data items at all. Okay, so I hope this figure makes this RC curve more clear. Any questions? So the rest is just some tips and tricks for training neural networks. So on the lectures on CNN, let's briefly review. So for classic computer vision, there are a lot of operations on images, mainly based on filters that are hand designed by researchers. So first, the image input image encoding. If it's a color image, then it's n by n by 3 tensor, where n by n is the image size and 3 is the 3 color channels. If it's a grayscale image, then you have n by n by 1. The color depth is the number of bits used to represent each pixel, each color of a pixel. So here you can see a color image decomposed into 3 channels, red, green, and blue. So the filters, or also called kernels in computer vision, is used to extract features from input images. So the specific operation is shown in the animation. So you slide the filter across the image, left to right, top to bottom, and output each element by the element-wise multiplication of the filter with the image patch in the input image. So in this particular case, you have 0 padding around the image. We'll see why 0 padding is necessary. So this operation is used to extract features for downstream tasks, either classification or regression. So here's an example of a filter for vertical edge detection. So if you work out the multiplication operation, this image patch multiplied by the filter gives you 0. And this image patch multiplied by the filter gives you 30, and so on. So the output is this image patch that's brighter in the center and darker in the on the two sides. So this is an edge. Therefore, this filter has extracted the edge feature from the input image. Similarly, this is a negative edge, where the center is darker and the two borders are brighter. So you can have another filter with 2 minus 2 instead of 1 minus 1 in the center, in the middle. Then your edge detector seems to work better, because the center is brighter. It's 40 instead of 30, whereas for the negative edge, the center line is darker, negative 40 instead of negative 30. So by the way, we have the negative values, whereas the normal pixel value is positive, but you can always do a normalization to bring it into a normal positive range. It's the relative values of the pixels that makes it an edge. So there are a lot of filters developed over the years by computer vision researchers for extracting various types of features. So these are so-called handcrafted features. But machine learning, especially convolutional neural networks, the goal is to replace the handcrafted features with learned features, learned filters. So instead of specifying the weights for the filter, you specify them as variables to be learned, parameters to be learned by training the neural network. So if you have low-level, simple tasks such as edge detection, this seems to be unnecessary. The edge detector we saw before works pretty well. In fact, if you train a CNN for an image classification task, the lower layers, the layers closer to the input actually will have the, you will recover some of the filters similar to the handcrafted features we saw before. Maybe not exactly the same, but with similar weights. So in that sense, the low-level feature detectors work pretty well. But for high-level features, more complex tasks, learning is essential to achieving good results. So this is the big picture for convolutional neural network. So it's a sequence of convolutional layers and pooling layers and nonlinear activation functions for feature extraction. So that's the feature extraction, followed by one or more fully connected layers for classification based on the extracted features. So here I show one fully connected layer with a softmax classifier, which outputs a list of 10 results interpreted as probabilities for each classification result. Here, this probability of 8 is highest, indicating a correct classification for this input figure that's a handwritten 8. So for in the CNN, every neuron in the conv layer has a local sparse connectivity to a small patch of the input volume. So it's receptive field. So each neuron covers a limited, narrow field of view. Whereas in contrast, each neuron in a fully connected layer has receptive field that covers the entire input volume. So for example, here, the receptive field for this filter is 3 by 3. Anytime it looks at the image, it always looks at a 3 by 3 patch. Either this patch, or this patch, or this patch. So it can never look at an area larger than 3 by 3. And parameter sharing means that all the neurons in the same conv layer share the same filter parameters, weights, and biases. So this helps reduce the number of parameters significantly compared to the fully connected networks, and gives translational invariance. That is, an edge can be detected regardless of its location in the image, whether it's here or here or here. So the convolutional filter will slide across the image, so it will detect this edge no matter where it's located. So this is important because when you take a picture and you want the image classification to work, that's independent of the translation specific position of the object in the image. So let's look closer at a convolution operation. So the operation slides the filter over the image spatially, computing dot products Wx plus d to generate an activation map as an output. So the input may be an input RGB image with 3 channels, hence steps equal 3, or intermediate activation maps generated by hidden layers of a CNN. So we use the terms input volume and output volume to emphasize that they may be 3D tensors. So the convolution operation is the result of taking a dot product between the filter with weights W bias B and the 5 by 5 by 3 image patch. So this is the filter size, and image patch size is also 5 by 5 by 3. And so the total number of dot products is 75 multiplies and plus a additional bias term. So for the after you have performed the convolution, at every position in the image, you generate one scalar value output. When you slide it across the image, left to right, top to bottom, you generate another activation map, 2-dimensional activation map, as a result of sliding the filter. So in this case, it's a 28 by 28 activation map by 1, because you just applied one filter. And then you may apply another green filter, a separate filter with different weights and biases to the same image. And you generate another green activation map for this filter. So multiple filters generate multiple 2D activation maps stacked along the depth dimension to produce the 3D output volume. So here we have one input volume and 2 filters, blue and green. So the blue filter generates the blue activation map, and the green filter generates the green activation map. So the output is 2 activation maps stacked together into a 28 by 28 by 2 output volume. So suppose you have 6 5 by 5 filters, then we'll get 6 separate activation maps, also called feature maps. We stack these up to get an output volume. You can call it, view it as an image, but it's really intermediate feature maps of size 28 by 28, that's the spatial dimension, and by 6, that's the number of activation maps stacked together. So this is the intermediate representation to be passed on to subsequent layers for processing, just like the input image. So here's an illustration. Suppose you have an input as a black and white handwritten digit 9, and if you apply this one kernel, you get one activation map as output. If you apply 3 different kernels, each kernel generates a separate activation map, extracting separate features. And you get a stack of 3 output activation maps. So here's a more concrete example. Suppose you have 3 filters. W0 extracts the vertical line from the input image, and W2 is designed to extract the horizontal line from the input image. So if you apply the 3 filters to this X1 image, then you'll get output feature map, 3 feature maps. This filter Z0, W0, B0 applied. Here we assume the B. I think I should make it more clear. Here, all the biases are assumed to be 0, so only the weights have effect. So this filter extracts this output feature map, activation map, and this filter applied to this image actually generates this activation map. You can see that it's pretty much featureless. It means that the filter is not effective on this image because this image does not have any horizontal line. Whereas this filter is really a smoothing filter. It essentially averages the neighboring pixels into one output pixel. So it outputs a kind of featureless activation map. But if you apply the same 3 filters on this image with a horizontal bar in the middle, then the Z1 extracts a meaningful feature. The activation map looks like horizontal bars, while these two extract, Z0 and Z2 extract meaningless features. So you can see that different filters are responsible for extracting different features, and maybe some filters will be more effective in extracting features on some images than others. So for example, here Z1 is specialized for vertical line features. Z0 is specialized for vertical line, whereas Z1 is specialized for horizontal line. So then it's, by applying the 3 filters to the same image, we can expect different filters to extract different features. So here's example of applying the filter to a RGB image with 3 channels, red, green, and blue. And then you can imagine this filter as a cube. So the filter always has the same depth as the input image, 3. So this cube will slide across the input volume, each one convolution producing one output. So you can see that there are 4 possible positions for the filter to apply to the input image, indicating 4 elements horizontally. Then you move it down 1 pixel, and in the next row you perform convolution and generate 4 other elements in the output. And if you do this, going down 1 row again, another row output, and going down another row as output. So in total you have 16 4x4 output elements. So this is still a 2-dimensional convolution, even though the convolution operation looks like a 3D cube applied to a 3D input. It's called a 2D convolution because when you slide it left to right and top to bottom, it's still a 3D sliding motion. Whereas for a true 3D convolution, you also slide it across the depth dimension. But here, because the depth of the filter is the same as the input volume, we only slide it in the 2D dimension. So suppose now you add another filter. So we saw that one filter, so this is one filter, applied to one input volume, generates one output activation map. Then if you have another filter applied to the input volume, you generate another activation map. So this is an important slide. So I highlight with this symbol. This means important. So each filter always has the same depth. That is 3 as its input volume. A number of filters always equals the depth of its output volume, which is 2. Okay, any questions? So the output is 4x4x2 output volume. I think maybe it's clearer if I make them in color. So yeah, I'll do it later. So yeah, just to highlight that each output activation map is a result of applying each filter. So here's another example convolution. This is a PyTorch code, nn.conv2d. Input channel is 2, output channels 1, kernel size 3 by 3, it means 3 by 3 because a kernel is typically a square. For 2D convolution, it's always a square. Assuming the biases are 0, then you perform the multiply of this the input multiplied by the filter and get the output for the output activation map. So notice the multiplication is this multiplied by this piece of the filter, this multiplied by this piece. So that's one, that's another term, you add them together.
I have one question.
Yeah.
Yeah, so this two input, it will go to the two different node in the convolution neural network, or the same node will process both the input data?
Oh, by node. What do you mean by node?
Like node, like the input, like in the last lecture you explained about that it hold the input data, right? Like when we process the data, it goes to as per the image, it shows that the both the input channel is the processing parallelly.
Right. So you can imagine that this is a sheet of neurons,
Okay.
and the weights may be a sheet of neurons. The output is a sheet of neurons. So the input, each neuron here you have two pixel values. Typically, it's 3 for color images, and if you mean a node, if you're meaning node as a neuron, then this is the mapping.
Okay.
Yeah.
I also have a question.
Sure.
In the convolution 2D function in PyTorch, you say it's using a 3 by 3 kernel, but on the earlier slide, it looked like it used a 3 by 3 by 3 kernel. So how many dimensions does the kernel have?
Yeah. So the kernel size here, it means the dimension. It's a 3 by 3 dimension, and the depth, that is the depth is always the same as the input volume, so it's not shown. So if the input volume has 3 channels, then the depth of 3 by 3 the 3 by 3 filter is always has depth 3. So I think I should make it more clear. Each filter.
Does that mean that each channel is treated the same?
Yeah, the channels are always matched up with the filter channels. Figure shows 2 3 by 3 filters, each depth 3, with depth 3. So so we often omit the filter depth in coding because it's determined by the input volume depth. So if this is 3, the filter always has a depth at 3. So when the PyTorch says kernel size is 3, it means 3 by 3 spatially. And the input is actually 3 by 3 by 2 in this case, because the input channels is 2. But we don't show it because it's implicit.
Okay.
Yeah.
That makes sense.
Yeah. So 1 3 by 3 filter, yeah. So here's another example of the only difference here is output channels is 3 now, which indicates that, yeah, I should highlight this. Output channels is 3. It means it has 3 filters. Whereas this output channels is 1. It means it's 1 filter. So the depth is always matched with the input volume. So that's the let's make it color matched. Yeah. So so here the input channel is 2. So the filter implicitly implicitly has depth 2. Depth 2. Depth 2. And because you have 3 filters, you implicitly have 3 output feature maps, activation maps. So the output channel is 3. So because of this implicit relationship between input channels and depth of the filter, and the number of filters and the number of output channels, if you specify in channels and out channels in the API, then the rest is just implicit. You don't specify anymore. Yeah, these numbers should be red. One should be red. Okay, so this is an important point. It's a confusing point also. So I hope you can understand it. So every filter generates 1 output activation map, and the depth of the filter is the same as depth of the input. Okay, this kernel size is really referring to the 3 by 3 because it's always a square, so it just says 3, but it's really better to say 3 by 3. So here's an example of filters and input images. So this is the 3 filters and input image with 2 channels. So in terms of PyTorch, so this is the this is one filter. This is another one. This is another one. So that's 3 filters, each one with steps 2. And the input image has it's one image with 2 channels.
Just one thing, the 2 channel, I thought of 2 weight and 2 bias. Is it right?
You mean the input channels?
Yes.
Okay, the inputs, you can think of them as pixels. And weights
Okay.
and biases are for the filters.
Okay. So in the previous, like if you go to the slide, you have given the input in channel equal to 2. Is that 2 weight and 2 bias?
No,
No.
the weights and biases are associated with the filters,
Oh, okay.
W and B. The input is maybe I.
Okay.
Yeah. So in here, the filters have these weights. It's a 3 by 3 filter with steps 2. So each filter has 18 weights. This guy has 18 weights. This guy has 18 weights. And each one has one bias. So the parameters is 19 times 3 number of parameters. So the whole filter has a single bias, B. The W is dependent on the size of the filter. So if you apply the filters to the input image with 2 channels, just do the multiply. This particular star you see often in textbooks and in articles, it means convolution. But in PyTorch, it actually means element. It means Hadmarker product. So it doesn't mean convolution. In PyTorch, you have to say .conv to do convolution. So there's a mismatch in notation. So here we use it to denote convolution. So here for the output element, you perform output feature map, activation map, you perform convolution of this channel of the weights and this input channel of the input, and this second channel of the weight and second channel of the input. So you can let's take say this convolution here, this image patch multiplied by this filter gets 0.5 because only the central element is 0.5. The others are all 0. And similarly for all the other convolution operations, then you get a 3x3 output. Every element is 0.5. Whereas for this convolution, if you multiply this guy with the input filter, you get 0. So everyone is 0 except the middle one. Multiplied by the filter is 0.5. So each filter channel generates one output activation map by convolving with one input channel. And you add them together to generate one output activation map. Similarly, for the next blue, the other one filter, perform the convolution, add them together, you get another output activation map. And similarly for the third filter. So now you have 3 output activation maps. You stack them together to get a 3x3x3 output volume. So one point that the beginners often get confused is that they may think of perhaps this is one output activation map, this is another. You stack them together to get 2 activation maps, but that's not correct. So for every application of the filter to the input volume, regardless of the depth, here depth is 2, could be 3, could be more. So the output is always a single activation map. It's only when you apply multiple filters to the input image, input volume, then you get multiple output activation maps. So actually we'll learn later in the lecture about separable convolution, which indeed generates one output activation map for every channel of the input volume and filter. But that's an optimization. That's a separate issue. But for regular convolution, you always generate one single output activation map for one single filter. So here's an example of what the activation map and filter look like. So this is after training. So you initialize all the weights and biases, the parameters of the filters to be typically random before you start training. After you train it on millions of images, then the filters start to contain some meaningful patterns. So these are the filters, 5x5 filters in the CNN after training. And suppose this is the input. This is the corner of a car, I think. And then every filter extract a separate activation map, separate different features. So this guy extracts this activation map, this guy extracts this, and this extracts this. So 32 filters extract 32 activation maps. from the same single input volume, input image. So just we saw before, maybe some filters are more effective in extracting some features. Some may be specialized for horizontal lines. Some may be specialized for vertical lines. Some may be specialized for curves. Some may, for higher level level layers, some may specialize for detecting human eyes or human legs, and so on. So you can imagine every filter as a specialized little guy extracting a specialized feature. So here just shows the convolution steps. So here's the 7x7 input 3x3 filter. Stride is 1, which means that you move over 1 pixel, left to right, top to bottom, every time you move the filter. So the output is 5x5 because, say, on the top position, you have five possible positions you can slide the filter. So the output is horizontally, it's 5, dimension 5. Vertically, you also have 5 possible positions. So its output is 5x5. So if you have 3x3 filter, stride is 2, then output is 3x3 because you have on the top position, on the the top 3 pixels, you have 3 possible positions to slide this filter every time moving by 2 pixels. Similarly for the vertical direction. So output is 3x3. So if you have stride of 3, then so initially you do convolution here and move over by 3 pixels, do it here. And then you cannot move anymore to the right because the stride is 3, so you move off the edge. Then you move down and move right. So what happens is that the rightmost and bottommost columns are not processed. This information is lost. So this is obviously not a good idea. So the solution is to add padding, 0 padding. So if you have a 7x7 input, 3x3 filter, stride 3, you add a padding around the 7x7 input to make it 9x9. And then it works now. So you have 3 possible positions at the top and 3 along the vertical direction. So output is 3x3. So this is an important slide. This is the formula for computing the output volume size for given input volume size and the filter size. So suppose the input volume is W1 width times H1 height times D1 depth. So typically we often have square shape. W1 is equal to H1. Then we use N1 to denote the size. but often we have a non-square shape because the image could be rectangular. Whereas the filter is always assumed to have a square shape. So that's why we only say the filter with a single number to denote its size. It's actually f by f. And then to get the output volume size, output W, the width, W2 is W1 minus filter size plus 2 times padding divided by the stride and plus 1. Similarly for the height. And depth of the output volume is the same as the number of filters, as we said before. So with parameter sharing, the total number of weights is f squared times d1. That's the number of weights. And you multiply by the number of filters, that's the total number of weights. And total number of biases is one filter, one bias per filter. So that's a total of k biases. So in the output volume, the d-steps slice of the size W2 times H2 is a result of performing a valid convolution of the D's filter over the input volume with a stride of 3 and offset by the D's bias. By this, I mean, they just mean adding the D's bias. So I repeat here that each filter always has the same depth as its input volume, and number of filters is always equal to the depth of the output volume. So it's common to have a stride as is 1, filter size f by f, and 0 pad as this number, because if you do this, you can work out the mass and get the output width and height equal to the input. So the output activation map has the same spatial size as the input. So it's called the same padding. It's used very frequently, very commonly in deep learning. So if f is 3, then padding is 1. F is 5, padding is 2. F less than 3, no padding. So these are the common settings in deep learning. K, the number of filters, is often powers of 2, 32, 64. It's not, there's no concrete hard reason for it. It's just a convention. And the filter size is often either 3 by 3 or 5 by 5 or 1 by 1. And stride is often 1. Padding is, if filter size 3 by 3, then padding is 1. Filter size 5 by 5, padding is 2 to have same padding. So you should remember this formula. So here's the example, just to apply the formula. So the input volume is 5 by 5 by 1. So it's a grayscale image and 3 by 3 by 1 filter. So F is 3, K is 1 because only one filter. Stride S is 1, then the spatial size is computed as 5 minus 3 divided by the stride 1 plus 1, which is 3. So depth is 1 because there's only one filter. So the output volume is 3 by 3 by 1. So even though the figure shows that you have this left to right, top to bottom computation, the convolution operations are inherently parallel. So you can do, bottom to top, or do this, or in random order. It doesn't matter what order you do it. All these operations are independent from each other. So it's inherently parallel. So it's ideally suitable for efficient implementation on parallel hardware, such as CPU and FPGAs. So every element computation is independent of the computation of the other elements. You can do them in any order. So here's the same padding example we saw earlier in the early slides. Input volume is 5 by 5 by 1 grayscale image, and filter is 3 by 3 by 1. And output volume is, now you add padding of 1 around the input image. So that's padding is 1. So based on the formula 2p, you add 2 here, and output is 5. So it's called the same padding because the input image is 5 by 5. The output image is again 5 by 5. So the input and output have the same size. Okay, any questions? So here's an example of stride 2. So input and the filter size are the same. Well, now we have 3 channels. So this is the input with 3 channels. That's one input. This is one filter. This is another filter. Notice that it has 27 weights and 1 bias for each filter. And the output volume, if you do the math, it's 3 by 3 because you're dividing by 2 by the stride. And you can work out the minus 3 is obtained by doing the convolution. This guy convolved with this guy. Yeah, let's take a the highlighted part. So let's do the convolution of this guy with this guy. I think this is minus 6. This guy with this guy. I think it's 3. And this guy with this guy, 1. I think it's minus 1. 1 minus 2 minus 1. Okay. Oh, this is 2. So add them together is -5. Is this guy. Okay. So this is a page from a course from UC Berkeley. So this page is very good, very comprehensive on the CNN stuff. So it has an animation here. To show you the detailed computation. So here's another example of 3 input channels, red, green, and blue, and 1 filter with also 3 channels. And if the input volume is n by n by 3, you can do the mass with a padding of 1. You can see that it's same padding. So output is also n by n by 3. N by n, I think I made a typo here. N by n by 1 because there's only 1 filter. Yeah. So here's an example of multiple filters. Input is 32 by 32 by 3, and you have 10 5 by 5 filters. So you get the output as 28. So number of parameters. So each filter has 5 by 5 by 3 plus 1. That's the bias, 76 parameters. So 10 filters, you have 760 parameters. So the information is pretty repetitive. The point is that you should be able to do the math, do the arithmetic. If I give you the filter size and input volume size, you should be able to get the output volume size. So from a neuron point of view, each neuron has this operation of weight times input plus bias, this convolution operation, and then it's typically followed by activation function we discussed before. So it could be a ReLU, could be a sigmoid. So this F is the nonlinear activation function. So if you have 10 filters, then for every input 5 by 5 patch of the input image, there are 10 different neurons looking at it and each extracting different features, resulting in 10 different output activation maps. So this is just a slight change. If you set the padding is 2, then okay, then you can do the math and get the output as 32. So it's common to have filter size 5 by 5 and padding size 2. Then you have same padding, and output is the same size, spatial size as the input. The depth is different because the field is determined by the number of filters. Number of parameters you can add up to 760. So a 1x1 filter is very common. So it performs a mixing of the input channels, then applies a nonlinear activation function. Can be used to reduce the number of channels, the depth. So the nonlinear activation function also helps to increase the model capacity. So here we see that this is a 1x1 filter with depths equal to the input volume depth of 32. Then when you perform convolution with a stride 1 no padding, then the output had the same size as the input, 6 by 6. And the depth is equal to number of filters. So essentially, this input has 32 channels. Then this 1x1 filter essentially performs a mixing of the input channels to generate the output activation map. So you may think maybe if the input has a single channel, say 6 by 6 by 1, then does it make any sense to perform the 1x1 convolution, 1 by 1 by 1? Oh, it doesn't make too much sense. People don't do it. I mean, you're just multiplying the input by a constant, right? But sometimes it makes a little bit of sense because don't forget the nonlinear activation function. So that's another function. That's another point of applying 1x1 filter. One point is mixture of the input channels. The other point is to have the additional nonlinear activation function. This increases model capacity. That is, the more nonlinear layers you have, the more non-convex, the more complex the function, the deep learning encoded function can be, and the higher the modeling capacity. So, typically, you only apply 1x1 filter to an input volume with more than one channels. So here's a 1x1 filter example. Suppose you have 56 by 56 by 64 input volume, and you have 32 1x1 filters. Then the output is 56 by 56 by 32, which is equal to the number of filters. Number of parameters, each filter has 65 parameters. So 32 filters, you have 2,000 parameters. Okay, so I think we should take a break. Okay, see ya. Okay, let's continue. So there are some more advanced convolution operations. So this is dilated convolution. So this is one dilated convolution is just a regular convolution. And two dilated convolution is when you add zeros in the middle between the elements, input elements. And four dilated convolution is you add additional zeros. So the reason for this is to increase the receptive field size without increasing number of parameters. So that is receptive field for look at this regular convolution, a 3x3. But with this two dilated convolution, it's 5x5. So that it means that each output activation map is a result of the convolution operation with a larger patch of the input. So it's looking at a larger input area. This could be useful for large, very high resolution input images. Then if you use the regular convolution, you may have too many parameters. But if you use dilated convolution, you can quickly reduce the size of the activation maps by using a relatively small number of filter parameters. So 3D convolution is when you slide the 3D filter along all the three axes with height and depth, instead of the 2D convolution we saw up to now, which is sliding it left to right, top to bottom. That's a two-dimensional convolution. Whereas in this case, you're sliding it across the depth dimension. So this could be useful for 3D images, such as medical CT MRI images, or point clouds from LiDAR. So for LiDAR processing, because LiDAR is 3D, that's a bunch of points distributed in the 3D space. So 3D convolution seems to be a very natural thing to do. But it turns out that it's not really practical because of the high computational load. If you do the math, the computation is enormous. So people have devised other clever ways of doing convolution, doing CNN on point clouds. So 3D convolution is not really used for LiDAR processing. So this is a useful trick for converting convolution to matrix multiply. So this convolution operation, you see this left to right, top to bottom sliding motion. That's good for CPU single core implementation. Just do a for loop, two for loops, a few for loops. So, but for a GPU implementation or FPGA implementation, they are really good at matrix multiplies. So if you can convert it, then you can directly use the large number of libraries. BLAS is a matrix library, and then you can easily implement these operations in parallel. So here's the conversion, very intuitive. So the matrix, if you work out the matrix multiply, so, right? So one by one, if you draw the correspondence, it exactly corresponds to this convolution with the upper left corner. right? W00, x0, W01, x1, and so on. And then the next row multiply corresponds to moving this input patch to the right by 1 pixel. If you work it out, W00 times x1 W01 times x2, W02 times x3. So the 4 rows of the matrix, when you multiply it with the vector, exactly is equivalent to doing the convolution. So this helps with the parallel implementation on hardware, very efficient, helps with the efficiency of the implementation. But the expense is the increased memory size for storing the weights, because this original kernel only has 9 3x3 weights, whereas in here you're duplicating the storage by 4 times. So it's a trade-off between the parallel implementation convenience versus the storage size. So let's move on to the other layers in the CNN, pooling and fully connected layers. So the typical CNN architecture has multiple layers, each consisting of a conv, pool, and nonlinear activation functions, typically ReLU, but maybe others. So conv, pool, ReLU, generating one output output volume of 6 activation maps. Another conv, pool, ReLU with 10 filters generates depth 10 output volume. So this is a typical architecture. Many variants are possible. For example, you may have multiple conv layers stacked together without pool and activation functions in between. And then you apply the pool and ReLU after the multiple conv layers. That's possible. So the reason to have the multiple layers is to extract features in an increasingly abstract manner. So it's a hierarchy of features. At the lower level layers, closer to the input, you extract lower level features such as edges and corners. And mid-level features, and is eventually at the highest, closer to the output layer, you have the high-level features, more semantically meaningful features. And then you apply the classifier, could be a softmax, on these high-level features to produce a classification result. So this is actually biologically realistic. The neuroscientists have discovered that indeed in the human visual system, the retina, the lower level neurons extract edges, low level features, and the neurons closer to the back of your head extract a higher level, more abstract features. So the pooling layer has a similar but different computation for the output size. So notice the the pooling filter always has steps 1 and operates over each activation map independently. Hence, input volume and output volume always have the same depths, D2 equal to D1. So this is different from conv layer. Remember? So let me put it here. So for the conv layer, the output volume D2, the depth is equal to K, number of filters. Whereas for the pooling layer, also called subsampling layer, the output depth is equal to input depth. So the common settings are filter size 3 by 3 by 1 because it has depth 1, and S stride is 2. Oh, I think another miss. Okay. Typo should be 2. Yeah. So for example, 2 by 2 filter with a stride S equal 2, no pad, the output volume, if you do this math, it's half of the original spatial size. So that's why it's called subsampling. So you're shrinking the spatial size. So here's a example of 2 by 2 max pooling. So you can have it should specify f equal 2 in the figure. So it's 2 by 2. Stride is 2. So if you do a max pooling, then you take the max element in each patch. So here it's a 6. The max element in this patch is 8. The max element in here is 3. Max in here is 4. Or you can do average pooling. So you take the average of the 4 numbers. 3 by 3, 5.3, and so on. So max pooling is more common, but average pooling is also sometimes used. So the basic idea is to summarize, to have a smaller activation map to summarize the input, more detailed activation map. So here's an example of pooling or subsampling, downsampling, where you have a larger input activation map or image. You downsample it to a half size activation map. So you may have overlapping pooling. So here I show a 3x3 pooling filter with stride 1, no path. Then you can do this math to get the output size n-2, and you're sliding the filter across with stride 1. So every time you take a max, so initially you take the max element of the among the 9, which is 9, and move over 1 pixel, and another 9, move over 1 pixel. Now the max element is 5, and so on. So it is possible to have overlapping pooling. So it's more common in practice to have a 3x3 filter with stride of 2. So a fully connected layer contains neurons that connect to the entire input volume with no weight sharing. So like this, fully connected, just literally. So number parameters is filter is the size and out the output layer size connect to input layer size n in is n in plus 1 times n out. So the figure is not very good because it's missing a bias in here. Yeah, with the bias, you have the plus 1. So first, you can see the receptive field size is the entire input size. This neuron is looking at the whole input. Could be very large input image. There could be multiple fully connected layers. So here we have 3 fully connected layers. Besides the last softmax layer, you can have 2 additional ones in the middle. Typically 2 or 3 FC layers are common. More than 3 is uncommon, but possible if you want to have it. So this is the formula for computing number of parameters in each layer. So for conv layer, input size, output size, and number of parameters is simply number of weights plus a single bias times number of filters. For pooling, 0. Pooling layer has no parameters. Fully connected layers has this many parameters. So in fact, in a large CNN, over 90% of the parameters are due to the FC layers. So let's look at a fully connected neural network. That is, from the input to the output layer, every layer is fully connected. Then what happens? First, the input image size cannot be altered easily. and then the more serious problem is the permutation invariance. That is, it cannot recognize geometry locality of input, hence not useful for image recognition. So look at this image, handwritten digits. If you scramble the input pixels, just put the pixels in random positions. So this is the permutation of this image 0. This is the permutation of image 1 with same collection, same set of pixels, but arranged in the random positions. And then they look the same. So this guy and this guy look the same to a fully connected network. Similarly, this guy and this guy look the same. Because it's fully connected, every input neuron is fully connected to every next layer neuron. So the positions of these neurons do not matter. Therefore, it cannot distinguish among this left meaningful figure and the right random image. Therefore, it's not useful for image classification at all. It's only useful for the last few layers for classification after you have extracted the meaningful features with conv layers. And also number parameters can grow very large. So in the CNN, typically only the last few layers, less than equal to 3 layers, are fully connected. And conv layers can handle images of arbitrary size, but not the last few FC layers. So in a typical convnet, you have a fixed number of input neurons. Say if you have a input with 10 by 10 spatial size, then you have 100 input neurons. But if you want to adapt your CNN to apply to a different size input image, it's very easily adapted. You just change the number of input neurons, and the convolution operation can work easily without any change, because it's scanning from top to bottom, left to right. So the changing the input size does not affect the convolution operation. And importantly, it's not permutation invariant. That is, it can recognize the 0, 1, 2, the digits on the left, but not the one random pixels on the right. And that's a good thing. So it can recognize a geometry locality of input. Translation invariance, that's a good thing. That is, if you move over the pixels to some direction, left or right or top or bottom, it doesn't make any difference. CNN can still recognize the digit. And also it has fewer parameters than the fully connected network, often called a multi-layer perceptron. So fewer parameters implies less prone to overfitting. So we can look at some case studies, starting from the most classic LeNet 5. LeNet is is done by Yang LeCun, who invented convolutional neural networks. So that's why the name is LeNet, named after his Le in the middle of his name. So the input is 32 by 32 by 1, the grayscale images of handwritten digits. And here it shows the layers. Convolution 5 by 5, get output feature map 28 by 28 by 6. So feature map and activation map, people use it interchangeably. Subsampling reduced to 14 by 14 by 6. And then another convolution, you get output of 10 by 10 by 16. So here it shows the input, filter, output, and number of parameters in each layer. So always remember that input depth and filter depth oh, I think I made a typo in here. Yeah, 2 by 2 filters. Oh no, so this is the pool layer, so that's different. For the conv layer, it's always equal. This guy equal this guy. And the number of filters in the conv layer is always equal to output depth. And finally, you have 3 fully connected layers. The final output layer has 10 neurons outputting the 10 softmax computed probability values. So here's the computation details. So pay attention to this line here. So conv layer maps from the feature map 5 by 5 by 16, this guy, to 120 feature maps of 1 by 1 by 120. So it's a convolution by a 5 by 5 filter. So 5 by 5 filter and the 5 by 5 input, you get output of 1 element for each convolution, each filter. And then you have 120 filters. So that's 120 total output elements. But if you look at the literature, many people write this guy as a fully connected layer instead of a convolution layer. So you can view it as a FC layer that maps from the flattened input of size 400 by 1 to output of size 120 by 1. So I have another lecture on, there's a slide on turning the FC layers into conv layers. Let me look it up. So suppose you have this 2 FC layers, similar to the Lynette. and you can convert it into a conv layer by setting the filter volume equal to the input volume. Then each filter generates a single output in the next layer. So let me so suppose you have so the input is 5 by 5 by 16, which is if you flatten it, that's 120 neurons. The output is 120. So if you do the full connection, fully connected layer, right? Now, from the perspective of one output neuron, it's looking at all the input neurons. So this particular neuron, say N1, is computed by multiplying each input element with a weight, finally add a bias. So you can view it as a convolution of this 5 by 5 by 16 input and another 5 by 5 by 16 filter. These two convolutions together generates a single element of N1. So we can view this output element as computed by a convolution operation with the filter volume equal to input volume, or you can view it as a fully connected layer operation of the weighted sum of all the input flattened 120 neurons. So that's 120 neurons. So it's essentially two different points of view with the exact same operations. So that's why if you look in the papers, sometimes people draw it as a convolution layer. Here, sometimes people draw it as a fully connected layer. But because the convolution filter size 5 by 5 by 16, 5 by 5, by 16 is the same as the input feature map size. It's equivalent to a fully connected layer in terms of the computations. Okay, I hope I didn't confuse anyone. So, I mean, you may ask, why do you do this conversion? They're equivalent. It turns out they're useful. This conversion is useful for very fast computation of sliding an entire CNN across the input. It's useful for detection of an object in the input image, but we'll discuss this later. So AlexNet is invented by Alex Krzyzewski and Jeff Hinton. So the input image is larger and in color, 227 times by 227 by 3. And the figure shows all the filter and activation map sizes. So finally, a softmax with 1,000 output probabilities. That's for the 1,000 classes in ImageNet. Number of parameters is 60 million, and it introduced a ReLU activation function. So the LeNet was using sigmoid. It turns out that sigmoid works well for shallow, for smaller CNNs like LeNet, but for deeper, larger CNNs, it suffers from the vanishing gradient problem, and the gradient cannot pass through the layers very well. So ReLU doesn't have the vanishing gradient problem. It's more suitable for deeper networks. So VGGNet is invented in 2014. So the figure shows the different, all the layers, filter, and map sizes. It's also for ImageNet. And this illustrates more graphically how the input is gradually reduced in size until the last few layers. So typically, the spatial dimensions are reduced as you go from the input to the output. 224 to 112 to 56 to 28, 14, but the number of activation maps, the depth of the output volume is gradually increased, so they get thicker. 64, 128, 256, 512. So that's a common pattern in deep learning. So here are the computation details. You should be able to perform this computation. It'll be covered in the exam. So even today, VGGNet is still widely used for image recognition tasks. And also VGGNet has this stacked 3x3 conv layers. So the reason to have this is to have the same receptive field as a 5x5 conv layer, but fewer parameters. Similarly, you can have 3 stacked 3x3 conv layers with a part 1 with receptive field of 7x7. L stacked 3x3 conv layers have RF of 1 plus 2L. So suppose all the volumes have the same depth d. They don't have to have the same size, same depth. It's just the assumption for the example. Then you can compute the number of parameters of a 7x7 conv layer as 49 times d squared. But if you have 3 stacked 3x3 conv layers, then you have 27 times d squared. And they achieve the same effect in terms of the spatial size. So here, the every output element is a filter obtained by say 5x5 filter, looking at the input image patch of 5x5, or it can be obtained by 3x3 filter applied to 5x5 input image, which outputs is 3x3, and apply the 3x3 to a 3x3 patch, a 3x3 filter to a 3x3 patch, you get a single element. So the input and output are the same, but the number of parameters is reduced a lot. So this allows you to have multiple layers of, say, in this case, it's 2 layers of nonlinear activation functions. It increases the CNN depth. So this increases model capacity without increasing the number of parameters, while reducing number of parameters compared to the original 5x5 or 7x7 convolution layers. Okay, I think, yeah, number of parameters in VGGNet is summarized here. So in this figure, we did not count the biases just for convenience, because biases do not affect the order of magnitude. They only affect the minor digits. And also VGGNet has a number of variants. What I showed in the earlier slide was the best performing variant called VGG16 with 16 weight layers. Weight layer, by weight layer, I mean the conv plus fully connected layer, not the pooling layers, because pooling layers have 0 weights. Okay, any questions? Okay, I think I'll stop today. I'll see you. Oh, right. Carla, do you want to say something?
Yes, I just mentioned that on Wednesday we will have a look at Colab and PyTorch. So there will be a more, what we call maybe lab kind of session where we run some code and try those things which you learn or showed today. So you're very welcome on Wednesday, the first hour. And next hour, I don't know what happens, but you know, I hope.
Yeah, next hour, I think I can finish the CNN lectures. Yeah, I think I can finish these remaining slides on Wednesday.
Yeah, sounds nice.
Okay, see you on Wednesday. Goodbye.
Yeah, bye.
Thank you. Bye.
Bye.
I have a question.
Oh, yes?
Are the lectures on, or is the lecture on Wednesday, will it be recorded? Because I won't be, like I have a schedule clash, so I won't be able to attend.
Yes, all the lectures will be recorded.
Okay, perfect. Thank you very much.
Okay.
Bye-bye.
Bye-bye.